That was weird. Uh-oh. Oh, all right. I guess we'll get started. All right, so the topic of today's lecture, and probably the rest of the week, maybe next week as well, is inheritance. All right, so inheritance is another one of these relationships between classes. In this case, though, inheritance is the strongest relationship that you can have between two classes. So inheritance is a relationship where one class is derived from another class. Right? So there's this quote here from the Java tutorials, right? I'll just quickly read it. So the idea of inheritance is simple but powerful. When you want to create a class, a new class that, and there's already a class that includes some of the code that you want. So that's kind of important right there. Include some of the code that you want. You can derive your new class from the existing class. In doing this, you can reuse the fields and methods of the existing class without having to write and debug them yourself. Right, so the idea is you have you know that you want to make a class, but there's another class around that's pretty similar to the one that you want to create. Right? So one way to create your new class is to use inheritance. It's not the only way, right? So we've already seen an example using composition, where you can use another class to provide most of the functionality for the class that you want to implement. Right? So for example, for a stack, you can just use an array list. Right? And if you use an array list using composition, you get most of the functionality that you need to build the stack just by using the list. Right? So inheritance is another way of doing this. Okay, so inheritance is actually item number 4 in this object model. So many weeks ago now, I introduced the object model. So I think when we started to talk about creating classes, right? So we've already talked about abstraction, encapsulation, and modularity. Right? The 4th pillar is hierarchy. And interfaces and inheritance are the Java mechanisms for supporting a hierarchy of classes. So a hierarchy of classes means exactly what you might imagine, right? There's some sort of organization of classes where something's at the top, right? So in the case of Java, every object in Java, or every class in Java, inherits from this class called object. Right? So we say every class in Java is a subclass of java.lang.object. Right? So for example, one of these might be string. Right? One of them might be, what would be a good one? Somewhere down here there might be array list, right? And so on and so on and so forth. But object is at the top of the Java hierarchy. Okay, so we need to know a little bit of terminology to talk about inheritance. So there's something called a subclass and there's something called a superclass. So a subclass, you also see it called derived class, extended class in Java, or child class. So child and derived are the generic. Child, derived, and subclass are the generic terms. So a subclass is a class that's derived from another class. Right? So in this picture here, right? A superclass or base class or parent class. That's the class from which a subclass is derived. Right? So here we've got X, it's the superclass, and here we've got Y, it's the subclass. Right? So Y is derived from X. So that picture there, that's a UML class diagram showing the inheritance relationship. Right? So the arrow points from the subclass to the superclass. Right? In UML, it's an open arrow like this, drawn as a triangle. There's a different type of arrow that indicates something else. So it's solid line, open triangle connecting the two classes. Right? So an example in Java would be object and string. Right? So object is the superclass, string is the subclass. So string is derived from object. Now the relationship is one way. Right? So string is derived from object. Right? Object doesn't know anything about string in this case. Right? So string knows everything there is to know about object. But well, that's not true. String knows about object because it's derived from object. Object does not know about string. Right? So as far as the object class is concerned, it has no idea what its subclasses are. Okay, so going back to this picture here, you can see that you can have a superclass and a subclass. This subclass can be the superclass for another class, right? So this is a subclass to that. And this class can be a superclass for yet more classes. So you can have this big chain of classes, all related by inheritance. Right, so in this picture here, A is derived from Z, right? Z is derived from X is derived from object. Right? In Java, the chain always goes all the way back to object. Right? So no matter what class you have, sitting above it somewhere, related by inheritance, is the object class. Right? So we say that a class is said to be descended from all of the classes in the inheritance chain, going all the way back to object. Right? So these classes, Z, X, and object, these are all ancestors of A. Right? For Z, X and object are ancestors of A, and for X, object is the ancestor of A. Okay, now why are we using inheritance? Or why are we interested in this idea? So in inheritance, a subclass inherits all of the non-private members. Right? So everything that's all the non-private fields and all the non-private methods are inherited from its superclass. That's actually not exactly true. It doesn't inherit the package private stuff. Okay. Anything public or protected, though, it inherits from its superclass. Right? So if there's an existing class that provides some of the functionality you need, you can simply derive a new class from the existing class. Right? And that prevents you from having to write a lot of code. Right? Because you can just take whatever the superclass provides and use that functionality. Okay, so your new class has direct access to the public and protected fields and methods of the superclass. Right? So if your superclass has any method or field that's marked public or protected, right, your subclass can just call that method. It doesn't have to do anything special. Right? It simply calls the method. If it wants to, it can redefine those methods. Right? So any public or protected method defined in the superclass, the subclass can redefine, right, or override. So that's why that's how overriding toString, equals, and hash code works. Right? Those methods are all public and object. So any class that you write, you're allowed to replace the definitions of hash code, equals, and toString. Now your new class, it's just a regular class. It just happens to be a descendant of another class. Right? So because it's a regular class, you can put your own methods and fields and constructors into the new class if you want to. Right? So you're allowed to add new information in the form of fields. You can add new behavior in the form of methods. Once again, in inheritance in Java, there's no inheritance of constructors. Right? So you're always rewriting constructors for all the subclasses. Right? But you'll see how you can call the superclass constructor probably next class. All right, so inheritance is the strongest form of relationship between two classes. Right? So remember the relationships we have so far. There's dependency. That's the weakest relationship. Right? Slightly stronger is association. Then there's aggregation and composition, right? Both stronger still. And now we have inheritance, which is the strongest relationship you can have. So inheritance models the is a relationship between classes, right? So that means string is an object, right? Array list is an object, right? A point to is an object, for example, right? In Java, is-a means that a class is substitutable for any of its ancestor classes, right? So for example, a string object is always substitutable for a big O object. And what that means is that a string object can do anything that a big O object can do. Right? So wherever you need a big O object, you can pass in a string reference and everything works fine. Right? Wherever you need a big O object, you can pass in a reference to any object and it'll work fine. Okay, so object is unique in Java. So it's the only class where there is no superclass. Right? Because it sits at the top of the inheritance hierarchy. Furthermore, it's the class from which all other classes are descended from. Right? So no matter what you want to do, right? When you make a class, you are constrained by having that class be descended from object. Right? So in other words, your class will always have all the methods that object has. Right? All of the non-private methods that object has. Okay, now we haven't actually said anything about extending or being descended from or being a subclass in any of the classes that we've created so far, right? So when we make a class, it's just public class blah, right? But I'm telling you now that everything's actually an object, right? So if you create a new class, but you don't explicitly state what the superclass is, right? Then the compiler assumes that the superclass is going to be object. Right? Okay, so in Java, a superclass can have many subclasses, right? So there's no limit on the number of subclasses that you can create using some other superclass object, right? But the other way around, right? When you go back up the inheritance hierarchy, right, a subclass is only allowed to have one direct superclass, right? So the only direct superclass for y is x. Right? The only direct superclass for z is x, and the only direct superclass for w is x. Right? So Java provides what's called single inheritance, right? Meaning that a class can only have one direct superclass. Other languages provide what's called multiple inheritance. So here, z is descended from y and w and x. Right? So in other words, z has two direct superclasses. Right? So you can do this in a language like C++, for example. So this is called multiple inheritance. Now, one of the reasons the designers of the Java language decided to only have single inheritance is because it solves or prevents some problems. One of them being the problem called the deadly diamond of death. Right? So if you actually Google that term, there's actually a Wikipedia page for that term. Right? So there is something called the deadly diamond of death. That's the picture right here. Right? And this occurs in programming languages that allow for multiple inheritance. Right? So here you can see that there's a diamond-like shape in the inheritance hierarchy. Okay, so up here, suppose x has some method f. Right? So let's pretend it's public. Right? Now y and w, they're the subclasses of x, so they can override f, right? So they can provide a new definition of that method f. Right? So there's now, at this point, right, there's now three definitions of f, right? X has one, y has one, and w has one, right? And now, if you say that z is the subclass of y and w, you now have to answer the question, well, what version of f does z get, right? Z can override f, in which case there's now 4 versions of f, right? If z doesn't override it, does it get y's version, does it get w's version, or does it get x's version, right? Who knows, right? So this is the problem that the other languages that allow for multiple inheritance have to solve. Right? Okay, so from a Java point of view, is-a, or is substitutable for, means that you can use a derived class instance. So you can use a subclass in place of an ancestor, right? In place of any of its ancestors, right? Not just the direct superclass, but any of the classes that it's related to via inheritance, right? So if you write a method and it takes in a big O object, you can pass in any reference to that method. Right? So here's some class. Here's some method. It's static. The fact that it's static is irrelevant, right? So it's static. It takes in a reference to a big O object, right? And it does something. It doesn't matter what it does, right? It does something. Okay, so to use this method, right, someone can pass in a string, right? Because string is an object, right? Or string is substitutable for an object. Right? I can make a set and pass in the set to the method. That works fine. Hash set is an object. Right? I can make a point2 object, pass that into the method, right? And that works fine too, right? Because point2 is an object. Right? This is why equals has a parameter whose type is object, right? So you can ask any object, are you equal to any other object in Java? The reason this works is because the parameter has type big O object, right? Which means you can pass in a reference to any object. All right, any questions so far? Okay, now what you have to remember when you're programming is that is-a, or is substitutable for, right, has no relationship whatsoever to the real world, right? So you're programming something, right? You're creating a class that does something. You want to use inheritance to create a second class, right? You have to remember that that relationship there is purely a programming construct, right? Nothing to do with the real world. So for example, not yet, I guess there will be, where's the, oh here, okay, the example's coming up, right? So is a, or is substitutable for, right? It's only related to how the implementer, so you, the programmer, right, has modeled the inheritance hierarchy, right? So the classic example, which you can find easily if you just Google inheritance circle ellipse, right, is circle and ellipse, right? So you can imagine you're creating an inheritance hierarchy of shapes, right? So somewhere at the top you've got a class called shape. Underneath that you have a subclass called ellipse, right? And then underneath ellipse you might be tempted to create the subclass circle, right? So that's the question you have to ask, right? So when you go to do this, right, you have to ask yourself, do I really want to do this? Right? In other words, do I really want to make this circle be substitutable for any ellipse? Right? So mathematically, so if you are living in the real world, you would say yes, right? A circle is an ellipse, right? Now, the problem is you're actually in the programming world, so you have to ask yourself, is there something ellipse can do that a circle can't? Because if there is, then I can't use inheritance to model the relationship, right? So if ellipse can do something that circle cannot, then circle is not substitutable for an ellipse, right? Because the circle can't do what the ellipse is supposed to be able to do, right? So even though mathematically a circle is an ellipse, right? Programmatically, you may not be able to, you probably should not. Okay, so mathematically, even though circle is an ellipse, in your inheritance hierarchy, that may not be the case, right? So ISA means you can substitute a derived class instance. So you can substitute a subclass object for one of its ancestors, right? So if circle can't do something that ellipse can do, then I cannot pass a circle object to a method that takes an ellipse, right? Because the method won't be able to satisfy its contracts. So here's an example of a method that's defined by ellipse, right? So there's a method called setSize in ellipse, right? So this lets you set the size of the shape, right? So it takes in a width and a height, right? It has a precondition that says the width and height must be positive, right? And the contract for the method says it changes the shape so that its width and height become the specified width and height, right? So if you have an ellipse and you call setSize with 1 and 2, then its width becomes 1 and its height becomes 2, right? That's what that contract says, right? So is circle an ellipse? Well, no, not if setSize, not if the contract for setSize says that the width and height get changed, right? So the contract for setSize says that the width and height of the shape will be changed to the specified width and height, right? If you do this for a circle, then you don't have a circle anymore, right? So here's the setSize method for ellipse, right? I can pass in 1 and 2. The method doesn't say it throws an exception, right? It doesn't, right? It says it actually changes the width and height of the shape, right? So if I now implement circle, circle gets the setSize method, right? It also inherits its contract, right? So the contract for the circle method setSize also says that it's going to change the width and height of the circle, right? Now, if you change the width and height of a circle to unequal values, you don't have a circle anymore, right? So your abstraction is broken, right? You've got a circle class where you can have circles that don't have the same width and height, right? So in this case, right, so if there's a setSize method that promises to change the width and height to the specified values, then you can't use inheritance to model the relationship between circle and ellipse, right? Circle has to be its own class unrelated from ellipse, right? Now, suppose there is no setSize method, right? So suppose there's no method in ellipse that circle can also satisfy. Sorry, there's no method in ellipse that circle can't also implement, right? So if a circle can do everything an ellipse can do, then that's fine. You can use inheritance, right? But you have to always ask yourself when you're implementing an inheritance hierarchy, right? Is this class really substitutable for the one that I'm inheriting from, right? If the answer is yes, then you can go ahead and use inheritance, Right? If the answer is no, you had better not use inheritance. Right? And we'll see more examples of that probably the next lecture or next week. Right? If you've been reading the notebooks, you've probably already encountered a bunch of examples. Okay, so here's a naive inheritance example. So I'm going to use inheritance in the way that you're not supposed to. Right? So we've seen a stack, right? You've seen 3 implementations of a stack so far. Right? I'm now going to show you a 4th. Right? So you know what a stack is already. I don't have to tell you what a stack is. Right? You know that a stack looks like a lot like a list because we actually used a list to implement a stack. Right? So just to remind you, when you push an element onto the top of a stack, right, that's like adding an element to the end of the list. If you pop an element from the top of a stack, that's just removing the element from the end of a list. Right? And so at this point you can say, hey, I've got this list class, array list or linked list, right? Why don't I just inherit from that? Right? And then I can reuse the add and remove methods to implement all the functionality that I need. Right? So I don't have to implement add and remove myself. Right? I don't have to add any fields, right? Because it's a list. Right? So I can just inherit from array list and make my stack. Right? So if I want to make a stack of integers, I can inherit from array list integer, for example. Right? So how does this look? Well, you import array list, because I need to use array list. Right? You make your class, so I'm going to call it bad stack, because this is going to be a bad stack. Right? Now, when you use inheritance, you use the keyword extends, right, to indicate what the superclass is going to be. Right? So bad stack extends array list integer says that bad stack is the subclass of array list integer. Right? So Java uses the keyword extends to indicate inheritance. Right? Okay, there's no fields in this stack class, right? Because array list already has all the fields that you need to implement the stack, right? Array list has all the storage you need for its elements, right? So there's no need to put in any fields here to store any extra values, right? The array list already provides all that functionality for you, which is why you want to use inheritance, right? Okay, how do I push an element onto a stack? Well, I add the value to the end of the list, right? Bad stack extends array list says bad stack is a list, right? What does that mean? It has all the list methods, so you just call add, right? So this add value and you're done. There's push, right? What about pop? Well, I want to remove an element from the end of the list, right? But bad stack is a list, so I can just call remove, right? And remove the element. This is great because remove even throws an exception for you if this size -1 is not a valid index, right? So I don't even have to do any exception checking, right? I don't have to do any error checking here, right? Remove's going to do it for me, right? And it'll throw an array index out of bounds exception for you if you try to pop an empty stack, right? So that's it. You're done, right? Yeah.
Why don't we just use this? Why does it bad stack?
I'm going to show you in a minute. I'm going to explain why in a minute, right? You're done. That's it. You don't have to implement toString. It's already there. You don't have to implement equals. It's already there. Hash code, already there. You're all done, right? That's like the easiest stack you can implement in Java, right? It runs, right? It actually works. So you make a bad stack. You can push some elements on it. I can print it, so you get 0, 1, 2. Right? Great. So when you're printing the stack, the 2 is the end element is the one that's on the top. Right? I can pop the stack, right? So pop. The 2 comes out, the 1 comes out, and the 0 comes out, right? And everything works just fine. If you pop the stack again, you get an index out of bounds exception, which is also fine, right? And that's it, right? You're ready. You're good to go. You can call equals, right? Compare 2 stacks to see if they have the same elements in the same order, and all sorts of other things. And that's the problem. You can do all sorts of other things, right? So why was this a bad idea, right? Because inheritance means is-a, right? So you're saying your stack is a list, right? What does that mean? It means anything that a list can do, your stack can do, right? Such as, right, I can get an element from the middle of the stack, right? Now remember, a stack, you're only supposed to get the element at the top, right? So everything on a stack is supposed to happen at the top of the stack, right? But now, because I've said that it's a list, I can grab an element from the middle of the list, of the stack, sorry. I can also set an element in the middle of the stack, right, which you're not supposed to be able to do. I can remove any element of the stack, right? So I can reach into the bottom of the stack and remove that element, right? And I can iterate over the elements of the stack, which might not be so bad. You might actually want to do that. If you implement it using inheritance, you automatically get it, right? You automatically get the ability to iterate over the elements, right? Unfortunately, you get all this other stuff that you're not supposed to be able to do, right? So for example, right, I can push 100, 200, and 300 onto a stack, right? And then I can get the middle element, right? So I can get element number at index 1, so that prints 200, right? You're not supposed to be able to do that with a classical stack, right? I can change the element that's in the middle of the stack, right? So I can set the middle element to minus 1,000. That changes the element in the stack to minus 1,000, right? So these are all things you're not supposed to be able to do with the stack. So using inheritance to implement a stack is an example of incorrect usage of inheritance. Unfortunately, it's very common, right? So inheritance should only be used when the is-a relationship actually exists, right? So a stack is not a list, right? It's not a list. It's not supposed to be a list, right? That's not the abstraction a stack is supposed to be providing. Therefore, you should not be using inheritance to implement a stack, right? Now, the funny thing about this is that even professional expert programmers, so people with many, many, many years of experience, get this wrong. So if you go look in the Java standard library at the class Java util stack, you will see that it extends from a class that's actually a type of list, right? It extends from the old list class in Java, right? So the implementers of the language did exactly what I just told you you're not supposed to do, right? And they've been regretting it ever since. So this is the classic Java example of what not to do when you try to use inheritance. Okay, so how should you implement the stack? Well, you've seen 3 other ways to implement the stack, right? Really, you should use the easiest way is to use composition, right? So your stack class has a list inside of it, right? And now it's almost as easy as the implementation back here, right? It's almost as easy. Oh, the other thing to know about this implementation, there's not even a constructor, right? You don't even have to redefine any constructors because the normal array list constructors work just fine, right? So if I say bad stack B equals new bad stack, right? It turns out that the compiler actually makes a constructor for you that works, right? So I don't even need to define a constructor here, which is the allure of using inheritance, right? It makes it really easy to create classes. But it also makes it really easy to create bad inheritance hierarchies. All right, any questions so far? Okay, so there's many reasons to use inheritance. One of the reasons that's often cited is that you want to reuse existing code, right? Presumably the existing code's already been tested and debugged, right? Widely used, hopefully. Right, so you know that it's already, so you're confident that it's correct, right? And so it's nice if I can reuse that code. Okay, now remember we were talking about this counter way, way back, several weeks ago now, right? You remember a counter is really simple, right? It simply counts. It just counts starting at some value going up, right? Our counter started at 0. It keeps counting until you hit integer max value, right? When you hit integer max value, it wraps around back to 0. Right? Now, you can ask the question, well, that's great, but what if I want a counter that does something else when it hits integer max value? Right? So what if I want the counter to stop counting when you hit the maximum value? Or what if you wanted to throw an exception or something else? Right? Okay, so here's the counter class, just to remind you what it looks like. Right? It's got a field called value. Right? The constructor sets the value to 0. There is another constructor that sets the value to some specified value, but it's not shown here. You can get the value, right? So there's a public method that returns the value of the counter, and there's advance, right? So this is the method that you call to make the counter go up by 1, right? There's the test to see if the value of the counter is not integer max value, right? So if it's not integer max value, you just add 1 to the value. Otherwise, If it is integer max value, you wrap around back to 0. Right? Okay, so if you want some other behavior for a counter when it hits integer max value, you can use inheritance. Right? So I can extend to the counter class, right? And I can override how advance works. Right? Now, this doesn't exactly work if we leave the counter class the way it is. Right? So notice up here, right, that field is private. Right? So if I use inheritance, right, if I inherit from the counter class, I can't access that field. Right? Because inheritance, in inheritance, you don't inherit the private fields of a class. Right? Which means I can't use, a subclass cannot use the field value directly. Right? That's a problem because here, right, if I change the way advance works, I'm going to have to set value to something. Right? Or I'm going to have to at least access the field called value. So now I have a problem, right? I can't immediately use inheritance without doing something about that, without being able to access that field. Okay. Right, so our subclass has no way to actually modify that field called value. Right? And this turns out to be a very common problem when you try to extend a class that was never designed for inheritance in the first place. Right? So when you use inheritance, you really should be trying to extend a class that was originally designed to be part of an inheritance hierarchy. Right? When we made the counter class, we didn't even know about inheritance, so there was no way to design it in a way that it would be usable in a hierarchy. Right? So this is a very common problem. All right, so if I want to use, so if I insist on using inheritance, I have to go into the counter class and modify counter. So let's do that. Right? So I have to make that field accessible to my subclasses, right? And that's exactly what this modifier protected is for. Right? So the protected access modifier allows a subclass to access the field, a field defined in a superclass. Right? A field or method, right? So that's the fourth access modifier in Java. Right? Public, anybody can use it. Private, nobody can use it except the class. Protected, only the subclasses and the class itself. And it turns out any other class in the package can use it, which is weird. That's the way it is. Package private, which is no access modifier, means only the class itself and any class in the same package can use it. Right? So protected is the second least restrictive access modifier in Java. Right? So I'm now going to go into counter and change the field, the access modifier to protected. Right? Now subclasses can access the value field directly. Right? Here's the other constructor now. Right? So I don't know why this is missing from the other slide. There's also a constructor where you can set the value of the counter to some initial value. Right? Okay. I now have another problem, right? So the counter class was never originally designed for inheritance. There was a contract on advance, right? So up here, right? That's what advance promises to do, right? When you call advance, right? So it promises that the value of the counter is set to 0 when you exceed integer max value, right? But now I want to change that, right? So the subclasses, I want to change that behavior, right? But remember, subclasses are supposed to be substitutable. So if this is the contract for advance, then it doesn't look like I can change that behavior without breaking the contract. So that's what I have to do. I have to modify the contract now. Right? So I have to modify the contract of advance to indicate that subclasses might change the behavior of the method. Right? So now I'm taking an existing class and I'm trying to adapt it so that it's usable in an inheritance hierarchy. Right? Okay, so it's easy to change the contract method, right? So I'm going to use counter as my superclass for all counters, right? So I can predict that that subclasses are going to want to change how advance works, right? So I can simply indicate in the contract that subclasses might change this behavior, right? And you're fine, right? So now anybody who's using this advance method, right, knows that, well, the generic counter is going to wrap around to 0 when you hit integer max value, right? But other counters might do something different, right? So that's my escape clause in this contract, right? That's what lets me change how this behaves in inheritance. Now the compiler is not actually going to check, right? The compiler never reads the comments, right? And it doesn't try to figure out how to ensure that this is true, right? So if you don't put this into your contract, I mean, the compiler doesn't care, right? You can write your subclass and everything will be fine, right? But anybody using the counter class will be upset, right? Or could be upset, right? When they end up with a counter that doesn't actually wrap around to 0, right? Because that's what you promised before. All right, so why are we modifying the contract? Because subclasses are supposed to be substitutable for their superclasses, right? That's the reason why. Okay, so now I can finally implement inheritance, right? So I can finally implement a counter that does something different when you hit max value, right? So let's suppose we stop counting, right? I want to stop counting when you hit integer max value, right? So I'm going to make a class called stopping counter that extends from counter. There's no fields, right, in the class because the counter class already has all the fields that I need to implement a stopping counter, right? All I need to implement the stopping counter is the value of the counter, right? And I already have that from counter, right? So you do not put in any extra fields here, right? In particular, you don't redefine the value field here, right? You do not reinsert a new value field here. Now, a subclass is allowed to add its own fields if it wants to, right? So if I want to, I can put extra fields into stopping counter class, right? The superclass never knows anything about the subclasses, right? So the superclass can never see the fields of the subclass, right? I don't have to add any fields in this case, right? But keep that in mind. Okay, I now need a constructor. Well, I don't actually need a constructor, but anyway, if I want to implement the constructor, I now have a problem. Well, I don't have a huge problem, right? I want this constructor to set the value to 0, right? Okay, so what is the purpose of any constructor? Right? The purpose of any constructor is to initialize the value of the fields of an object, right? That's the purpose of the constructor. So I'm now in a situation where I'm trying to set a field that actually lives in the superclass. Right? I want to set the value of the counter, but the value field is defined up in the superclass. Right? So how do I access that field? Well, it's protected. Right? So if I wanted to, I can just write this dot value equals 0 here if I wanted to. That would be fine. Right? Because I am allowed to access that field directly by name. Right? The other way to do it is to call the superclass constructor. Right? I want to call the superclass constructor and have the superclass constructor set the value of the counter. Right? Now, if the fields that you need to set in the superclass are private, then calling the superclass constructor is the only way that you can set the value of the fields. Right? So there are situations where you must call the superclass constructor, right? Because the superclass is going to initialize fields, possibly fields that you don't know about because they're private, right? Okay, so the way you call the superclass constructor is with the keyword super. So super, round brackets, calls the superclass no argument constructor, right? So in other words, it calls the counter constructor that has no arguments, right? The counter constructor will now set the fields for the counter. Okay, so there's a bunch of rules for writing constructors and subclasses. Right? Rule number 1. Right? The first line in the body of every constructor must be a call to another constructor. Right? So we haven't done this in any of the classes we've created so far. Right? But rule number 1 actually exists. Right? The very first line on any constructor is a call to another constructor, right? In particular, it's a call to the superclass constructor, right? So remember rule 1, right? Okay, if that call is not there, the compiler puts it there for you, right? So we've never tried to call another. Well, we've done constructor chaining, right? But we always get to eventually we get to a constructor where there's no constructor call in the first line, right? when the compiler sees a constructor that has no call to the superclass constructor, it sticks one in for you. Right? In particular, it tries to call the superclass no argument constructor for you. Right? Now, that's a problem, because if the superclass no argument constructor doesn't exist, or if it's private, right, then the compiler stops with a compilation error. Right? Okay, so if the superclass does not have a no argument constructor, then you have to call some other constructor manually yourself. Right? But we'll get to that in a minute. Maybe not today. Okay, now, if you decide you want to call another constructor, right, in your constructor, then the only place you can do that is on line 1. Right? So rule number 1 says the first line must be a call to another constructor. Rule 2 says if you're going to do it, it has to be on line 1. Right? 3, at some point in time, right, the superclass constructor has to be called. Right? So in a subclass, right, the subclass constructor must eventually call the superclass constructor somehow. Right? Usually it's on line 1. Right? Now, you don't have to call the no argument constructor. You can call any of the superclass constructors. Right? So we'll see examples of that shortly. Right? So remember these 3 rules. Right? Line 1, rule 1, first line should be a call to a constructor of some kind. 2, when you call a constructor inside another constructor, it has to be on line 1. And 3, at some point you have to call a superclass constructor. Right? All right, so keep those rules in mind. We're going to get to those probably, we'll see examples of those, I think maybe later today. And if not today, tomorrow, on Friday. Okay, so our second constructor, right, initializes the counter to a specific value. Right? So now what goes here? Well, rule 1 says I should call some constructor, right? So there's a few ways you can go about doing this, right? So I am allowed to use constructor chaining still if I want to, right? So in other words, I can call another stopping counter constructor from any other stopping counter constructor, right? So this blah, right, I'm allowed to do, right? Whenever we've done that, that's always been on the first line, right? Okay, so rule 1 for the constructor says that the first line of the constructor must be a call to another constructor, right? That's what lets you do constructor chaining, right? It doesn't have to be a call to the superclass constructor, right? Eventually, you have to call the superclass constructor. It doesn't always have to be on line 1. It doesn't have to be, if you're using constructor chaining, right, you're not calling the superclass constructor immediately, right? You're going to let another constructor call the superclass constructor. Right? Okay, so for example, right, instead of calling the superclass constructor, the superclass no argument constructor here, right, I can chain to that constructor here. Right? So we've seen chaining already. This is fine. Right? Because line 1 is a call to another constructor. So that's good. Right? That calls this constructor. Right? Now rule 3 says a superclass constructor has to be called at some point. So when this constructor calls this constructor on line 1 calls the superclass constructor. Right? So this constructor is fine. Right? Because it eventually results in the superclass constructor being called, right, and the value being set. Right? This constructor is fine because you're calling a constructor on line 1, and you're calling the superclass constructor. Right? So that takes care of rules 1, 2, and 3. Right? And we're good to go. So there's your stop. That's one way to implement the stopping counter constructors. Right? You don't have to do it this way. Right? You can write this dot value equals 0 here, right? And you can write this dot value equals value here, and it's still fine. Right? Why is it fine? Because if you don't call the constructor on the first line, the compiler calls it for you. Right? So if you write this value equals 0 here, Right? So if I write this value equals 0 on line 1 of that constructor, right? Then the compiler silently puts in here super. Right? That'll be added by the compiler automatically. Right? Which forces the superclass constructor to be called. Right? Similarly, if you write this value equals value here, then the compiler silently inserts that for you. Right? This only works assuming this constructor exists, right, and is not private. Right? But if you, but you can implement this that way as well. Right? Similarly, you can use the chain to here, right, and then down there you can write this value equals value, right, and that's fine too, right? They all work. However, you should get used to, when you're in an inheritance hierarchy, you should get used to calling a superclass constructor on the first line, or using constructor chaining on the first line of every constructor. Okay, so the next part is going to be, I think it's going to be an explanation of why you have to do this. So I'm going to stop there because it's already 1:15, and the explanation is a little bit longer than 5 minutes. All right, so I will see you again Friday morning. Oh, there was a, if you didn't see the announcement on OnQ, there was a small change to assignment 1. It's not a change. There was an explanation of what to do in the bit class that was added to the assignment. So make sure you look at the updated assignment if you've already submitted it.